Hello there, and welcome to our lesson in Math 101. Our lesson is logic. Okay, of course, Math 101, or the descriptive title of our course is Logic and Set Theory. So the first part would be logic, and we have our first topic for this lesson. We have propositional logic. But before that, let us define what logic is. I guess we haven't really defined it, and this is one of the advantages of using or advantage of an online class. We can just simply um, use Google here and type in logic in simple words. So you have here in simple words, logic is the study of correct reasoning, especially regarding making inferences. It began as a philosophical term and is now used in other disciplines like math and computer science. So you guys taking a math course or a math related course or a computer science related course, then that's why you have this Math 101 class. Well, the definition sounds simple enough. Understanding logic is a little more complex, but don't worry about this. This is why you are enrolled here in our subject. So this complex thing here becomes simple for you to understand. And I don't know if you can see this simple or this small picture here. That is an example of a formal logic. You have here, all spiders have 8 legs. Black widows are a type of spider. The conclusion here is black widows have 8 legs. Okay, let's go now to our lesson. We have propositional logic. Outline for our lesson would be we were going to define propositions, then logical equivalences, then we have normal forms. All right, let's define what a proposition is. A proposition is a declarative sentence that is either true or false. If your English lessons are fresh, declarative sentence always ends with a period. It declares something, you state facts or opinions there. So for it to become a proposition, it should be either true or false. You have here some examples of propositions and some examples of not propositions. So the first five, let's go over to these five sentences here and see why they are propositions. Number one, the moon is made of cheese. Of course, that's a declarative sentence and it is false. Second, Iligan is the capital of the Philippines. That is false. It's a declarative sentence. It makes it a proposition. Tokyo is the capital of Japan. That is true. Proposition. You also have, oh, sorry. You also have here, it does not end with a period because it's in a mathematical form or mathematical symbols. But if we're going to rewrite this into words, then it will also be ending with a period. And that is either true or false. In fact, the first one here is true. 1 plus 0 equals 1. Okay, and 0 plus 0 is equal to 2. Okay, the next examples are not propositions. Why? Take a look at the first one. Sit down. You can never say this is true or false, and it ends with an exclamation point. So it can never be a proposition. What time is it? It's asking for time. You cannot say it's true or false. So it's not a proposition. The last two examples are in mathematical symbols. Well, this may end with a period similar to the previous examples, but these are not propositions in the sense that you can also never tell whether these two are true or false because these two equations contains variables and variables takes random values. I mean, you can have this one, you can, in the first example, x plus 1 equals 2, you may substitute x by 1, and that makes this a true sentence. But then you may also substitute another value other than 1, making this a statement false. So this would be true for some, false for some. Okay, that is also true. That is also true for the next example there. So these are not propositions. So we have here to construct propositions. Let us. This is describing propositions here. Propositional variables. We represent propositions by usually logic books would use the small letters P, Q, R, S, and so on. T, U, V, something like that. And propositions that is always true is denoted by capital T, and if it is always false, it is denoted by capital F. Compound propositions, meaning you have two propositions combined using logical connectives, and these are the following. So the first one, well, this might be used to one proposition, and it will change the sense of the proposition. I mean, if it is true, it will change to false and false to true. You have negation. You also have a conjunction that combines two compound propositions. Conjunctions. This is the symbol for conjunction. Disjunction have this symbol here. Uh, Implication implies or if then, and then the biconditional proposition or connective you have here. Okay. First one on the list is disjunction. So disjunction in English or in words, disjunction is represented by or. Okay, or it is either. So either or. So but in mathematical symbols, this one is used. It's like a V. Okay, so this is the truth table for disjunction. Notice here that you have propositions P and Q. Now, why do you have T T F F here and T F T F? This is how we construct this table so that we exhaust all possibilities in pairing P and Q. Remember, proposition can be either true or false. So if we just combine the propositions P and Q, the possibilities are P is true, Q is true, P is true, Q is false, and P is false, Q is true, and P is false, Q is false. So this exhausts all possibilities for combining P and Q. Now, what's interesting is the disjunction P or Q has this truth table given these conditions for P and Q. In the first row, we have if P is true and Q is true, then the disjunction of P and Q or P or Q, we have the disjunction PQ there, is true. I have to be very careful with and on the words or. Okay, if you also have a true P and a false Q, then you have a true disjunction. A false P and a Q true, you also have a true disjunction. And if a false P and a false Q, you have a false disjunction. This is very easy to memorize how this disjunction of proposition table or truth table is constructed. I hope you have noticed by now that the disjunction is true whenever one of P or Q is true. So if you have a true P or true Q, just one of them, and it makes the disjunction true. Of course, if both are true, we only need one, then it is true here. So that is why in the last row, you may observe that false and false there. You don't have a true proposition here, so the disjunction is false. Even if you extend this to five propositions, combine them with this connective, or then, for example, you have five propositions there, four of them are false, one is true, that proposition is, or that disjunction of these five would be true. So if you take an example for this, say 1 plus 1 equals 0, or um, Manila is the capital of the Philippines. So Manila is the capital of the Philippines. So uh, that makes the entire proposition true, or the disjunction true, because Manila capital being the capital of the Philippines is true, even though 1 plus 1 equals 0 is false. But then you already have one true proposition there. The disjunction becomes true. Right? Let's go to its partner, the conjunction. It's an inverted, the symbol is inverted. It's a V, it's like an inverted V here. So these are the truth table. Now, for conjunction in words, this is and. So you have P and Q. Um, we have this true P, true Q, you have a true conjunction. True P, false Q, you have a false conjunction. A false P and a true Q, you have a false conjunction and a false, false, false. All right. So it's also easy to memorize this. Conjunction is very strict. Okay, you may view it like this. Conjunction is very strict. It can only be true when both of P and Q are true. For disjunction, it's not so strict because you only need one. For conjunction, you need both of them to be true. The rest is false. Okay. Next is implication. So you have, if P and Q are propositions, then P implies Q is a conditional statement or implication, which is read as if P, then Q. Okay? If P, then Q, and has this truth table. All right. This is as well easy to memorize. You have here T, T, you have a true, P implies Q, T, F, false, F, T, true, F, F, you have a true. So there's only one instance wherein this P implies Q is false, and that is you have a true P and a false Q. So before we discuss this truth table here, we have here in P implies Q, or if P, in this P implies Q here, P is the hypothesis, the antecedent or premise, and Q is the conclusion or consequence. Now, this is also very important. Implication can be expressed by disjunction and negation, and I believe that this will be very useful to you in the last section of our discussion today. You have there transforming statements or propositions into the normal forms. You will surely need this one because this transforms an if then statement or implies into a disjunction. Okay? So let's go back to our truth table for implication. Remember, the only instance wherein this is false is you have a true hypothesis or premise and a false consequence or conclusion. Okay, so understanding this, you have in P implies Q, there does not need to be any connection between the antecedent or the consequent. The meaning depends only on the truth values of P and Q. This implication is perfectly fine, but would not be used in ordinary English. For example, if the moon, so we should not use this in ordinary English, or else you will sound off. Okay, for example, if the moon is made of green cheese, and that is false, then I am an MSU IIT student. So you are an MSU IIT student. So you have this statement: a false, moon is made of green cheese, and then true. Now false implies true. If you can recall here in the third row, false implies true is true. So let us hear you again. If the moon is made of green cheese, then I am an MSU IIT student. So if this is a true statement, okay, or true proposition. But in English language, it will sound off because you will, of course, your ears would get sucked in by this statement, moon is made of green cheese, and you would then say, oh, that must not be true. Okay, but in logic, this is true. Okay, to understand the truth tables better, you have this example. One way to view the logical condition or logical conditional is to think of an obligation or contract. So here we have this statement or proposition: if I am elected, then I will give you 1 million pesos each. So P here is if I am elected, Q is I will give you 1 million pesos each. Okay, let us now consider the cases. You have the cases here: TT, TF, FT, and FF. All right. So, okay, you have first, let's consider true and true. For example, I am elected really, and then I gave you 1 million pesos each. So that is the case where everyone is happy. I won in the election, and then you received 1 million pesos each. Everybody is happy. Okay, we skip this false one. Let's go to the third row here. False implies true. Okay, first, I was not elected because false. You have here false. I was not elected. I did not won. Maybe you guys did not vote for me. But then I still gave you 1 million pesos each. So you are still happy here in this scenario because I still gave you 1 million pesos. Okay? No one or none of you will be mad at me because though I did not won, but I still give you 1 million pesos. Okay, so the last one here, or in the last row, we have a false and a false. For example, I said this to you. I promised you that if I won in the election, I will give you 1 million pesos. I did not win, so I did not give you 1 million peso each. So I guess none of you would really be mad at me because I didn't won. Okay? Now what could be perhaps be the case that you will surely be mad at me and you would surely call me a liar here? Of course, that is the second row, which is true P and false Q. See, you have if I am elected, then I will give you 1 million pesos each. I won. And then, oops, I'm sorry. I'm not giving you 1 million peso each. So if some of you would not receive, of all of you or all of you, then surely you will be mad. Okay? So you can consider uh, if then or implication as a obligation or contract or a promise. For example, you someone or a boyfriend promises her girlfriend to marry her if he gets a job. Say so. Let us construct the statement here. You have if I get the job, then I will marry you. In all four cases, the girl will cannot be mad at the guy, except for the case where he got the job and then he did not marry her. Okay, so this is one way of understanding implication. Okay. Now we have different ways of expressing P implies Q. Here, I'm not reading all of it. You can pause the video and memorize or be familiar with all of these things. Okay, let's proceed. Now we have the converse, contrapositive, and inverse. So the Q implies P is the converse of P implies Q. Not Q implies not P is the contrapositive of P implies Q. And not P implies not Q is the inverse of P implies Q. So for example here, find the converse, inverse, and the contrapositive of this proposition. It is raining is a sufficient condition for my not going to town. So it is raining is a sufficient condition for my not going to town. If we go back to our lists of restated implication here, we have uh, a sufficient. You have here the um, you have here one, two, three, four, five. The fifth from the top, P is sufficient for Q. So it's like the same as P implies Q. So this is P implies Q. So in our example, your P is of course it is raining, and then your Q is I am not going to town. All right. So that's why if you take the converse of this, then reverse, right? You can see here Q implies P. The roles of P and Q are just we exchange the roles of P and Q. So we just simply exchange them. If I do not go to town, then it is raining. For the converse, or for the inverse, the previous one was the converse. For the inverse, you have here the third one. Inverse, the roles are not changed, but then you put in a negation for each of P and Q. So I just put not here. So this is not. If it is not raining, then I will go to town, because here you already have um, a negated statement. So not going to town, if you put a not, then it means to say go to town. Okay. You have the contrapositive here. Contrapositive is of P implies Q, would be switching the roles of P and Q and negate them. So you have a negated one here. You negate also well. So you have if I go to town becomes go to town. Then it is not raining. How do the converse, contrapositive, and inverse relate to P implies Q? Actually, this symbol here is not yet discussed, but this is logical equivalence. Okay, and The correct one here is that for P implies Q, what is logically equivalent to for P implies Q here is the contrapositive. Okay, the contrapositive here is the so none of these three. I don't know. We have a fourth. We don't have. So it actually contrapositive has um, the is the logically equivalent to our P implies Q. We can verify that as well in truth tables. Okay, last one is biconditional. This is just a double if then. So to give you an idea, it's two if then combined with is a conjunction. Okay, a conjunction of two if then. But then you just switch. So you have P implies Q and Q implies P. All right. So that is that. I hope that you understand that, so that you will be it would be easy for you to understand this truth table here. Now take a look. Remember in P implies Q, it is only false when you have a TF. All right. And in the conjunction, both should be true for it to for the conjunction to be true. So if you have P implies Q and Q implies P, now the moment you get a TF or the TF in the other direction, then you get a false. All right? You get a false because this is P implies Q and Q implies P. In other words, for the first row, this will always be true. For the first implication, P implies Q, T implies T, that's true. Q implies P, that is also true. So true and true is true. For here, you have true implies false is false, and false implies true, that is true. But then you already have a false previously, so that's a false conjunction. You have false implies true is excuse me, false implies true is true, but then true implies false is false, so the conjunction would be false. Here, none would be false here. False implies false is true, then true and true, you get a true conjunction. So remember, that is the meaning of P if and only if Q, or the biconditional. This is just a conjunction of P implies Q and Q implies P. Or in other words, if you just simply memorize this as it is, not considering the conjunction, you might say that if these two guys here, I don't know if it makes sense, but if these two PQs here have the same sense, true, 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 false, false, true, then it will be false otherwise. Okay? So this is how you read a biconditional statement. You can pause the video and just simply take a look at it. So you have here vice versa and conversely. So that's why you have that and there. P implies Q and Q implies P. You have precedence of logical operators. So first you have negation, then conjunction, then disjunction, then implication, then the biconditional statement. So take a look at this. P or Q implies not R without any parenthesis here is equivalent to this, because if we consider the precedence, meaning ang pagkakasunod-sunod, that is in the Tagalog, the order, right? Precedence. What comes first? So this one, not R, of course, comes first. So that's why it's here. Okay. Then there's no disjunction. There's no conjunction here. So this is the meaning of it. Okay. If the intended meaning is this, then parenthesis must be used. Okay. If the intended meaning is that Q implies not R, you have this, Q implies not R, then you should not remove the parenthesis. Otherwise, it would mean this one. Okay. Next, we have satisfiability, tautology, and contradiction. A proposition is satisfiable if its truth table contains true at least once. So remember, getting a true at least once in the truth table, that is the statement or the proposition is satisfiable. Proposition is a tautology if it is always true. Example, P or not P. Of course, remember, a disjunction is true whenever either of them is true. So of course that's a P and a not P. So when you negate a P, the truth value becomes, or the truth value will be reversed, as I've said. So each of this, or in these cases here, you will also you will really get one of them to be true. So that's a tautology. A contradiction is always false. Now here you have the conjunction now of P and not P. Of course, they could not be the same. So the case wherein both are true cannot be is not possible. So you will always get a false conjunction here. So contradiction. A contingency if it is neither a tautology nor a contradiction. So not a tautology nor a contradiction. Okay, let's go to logical equivalence. Two compound propositions P and Q are logically equivalent if the columns in a truth table giving their truth values agree. This is written as in this symbol. I believe that you guys have this in your high school lessons or previous math lessons, determining whether statements are logically equivalent using truth tables. So if their truth values agree, they are logically equivalent. It is easy to show that P is logically equivalent to Q if and only if P implies if and only if Q is a tautology. Now you have the De Morgan's law for logical equivalences, or I mean De Morgan's law for this. You have a not, a negation of P and Q that is logically equivalent to not P or not Q. What happens here? It seems that the negation has been distributed here, and then the sense or the conjunction was changed to disjunction. That is as well true for the second one. Negation has been distributed and changing this disjunction to a conjunction. So you can view it as well left to right and right to left. No, you can remodel. You can rewrite this one with this because these two are logically equivalent, meaning their truth tables agree. Take a look at this. Well, you have what are involved here. You have not P, not Q, and these two. So you have there P. This is the truth value for P. TTFF for Q. TFTF. These two already exhaust the possibilities for P and Q. Well, of course, guys, remember if you've got three letters here or three propositions involved, to exhaust all possibilities, you need 8 rows. And P, for example, PQR, you're going to construct a TTT, 4T's, 4F for P, and 2T's, alternating 2T's and 2F for Q, and then TFTF for R to exhaust all possibilities, considering 8 rows there. So, well, here, let's go back to our example. You have P, TTFF, Q, TFTF. So your not P is just the opposite of P here. True, false, true. If this true here, false, false, true on the other. Not Q is the opposite of Q here. Now, for P implies P or Q, then you focus on these two, considering the disjunction here. So true or true, you get a true. True or false, well, true, we only need one true there. False or true, that is true. And false, false, that is false. Okay, and for this one, I think we're going to simplify this. So this one first, you have the negation of P or Q. So we negate this. That's why they are opposite. True, false, true, false, true, false, and false, true. Now, we are saying that this one here, the negation of P or Q, is logically equivalent to this. So we're actually showing the second statement. Um, you have, this is the disjunction of not P and not Q. So uh, this one should agree with this. Okay, first, the conjunction, sorry, of not P and not Q. You take a look at the columns for not P and not Q here. And remember that conjunction is true whenever both are true. So here you've got a false and a false, false, false and a true, false, true and a false, false, true and a true. That's only true. Now, if you take a look at the two tables here, do they agree or are they identical? Yes, they are identical to each other. Therefore, this statement here must be logically equivalent. Check. Okay. For this, I think you might want to show it. You might want to try it and show it, because in our exam, I'm going to let you show whether two propositions are logically equivalent using truth tables as well. So another way of showing truth tables would be not using, or I'm sorry, another way of showing logical equivalences or proving that two propositions are logically equivalent. There is another way other than the truth tables, and it uses these logical equivalences. Okay, so first you have the domination laws. You can pause the video here and take a look at all these logical equivalences. So so if I'm too fast, you can pause it. We have the domination laws, meaning you have P or T. The P will be dominated, or yeah, that's it, dominated by T, it becomes a T, something like that. And for false, it should be a conjunction. P and F becomes F, is logically equivalent to F. Identity, meaning it's preserved. P and T, it will just be P. P or F is P. Idempotent, this is for idempotent. For double negation, we have discussed this. Not and not, it becomes P. This is it is not, oh, I am not going to town. So if you negate that, go to town. Negation laws, P or not P is true. We also did this. P and not P is false. So you have commutative, associative, distributive, and absorption. Each of these words here, actually, these words that are used: domination, identity, idempotent, double negation, commutative, associative, distributive, absorption, are they have reasons why these words are used here. It describes the process. For example, absorption. Something has been absorbed. Take a look. You see, it is absorbed here. So it seems like this P and Q has been absorbed to P. You've got a P, and you can also view distributive. So your P here, P and or here is distributed over this uh, proposition. So P or Q and P or Q. So that's what is happening there. Associative as well, commutative. So P and Q, Q and P. All right. More logical equivalences. Well, you can also view the PDF that I have uploaded in our mole, so that you can study this one. Using these logical equivalences, you can also prove whether two propositions are logically equivalent, and this will be part of your exam as well. So you have to memorize these logical equivalences. All right, you have to prove this one. Mhm. We need to use, or to prove this actually, is either we show that the left would be, would you can apply the logical equivalences to either the left, showing it that it will become similar to the right, or the right to the left. In this example, we have the complicated going to simple. So I think that is one technique there. Complicated going to complicated, simplify it, making it simple. Then it is easier to do that than making a simple one to become complicated. So that's, well, it depends, but mostly that would be the case, right? So you have here, for the left side, we apply the De Morgan's law. Can you see the De Morgan's law here? Yes, this negation has been distributed here, not P, then to this 2 here, it should be distributed, changing this to and. Yeah, that's what happens here. Not P, and the negation of this. And then the next is De Morgan's first law applied to this one here. We distribute this, negation here. All right, so you've got there, and then change this into disjunction, not Q. And then double negation law, this one becomes positive. I'm sorry, becomes P. Yeah, I can view this as negative times negative is positive, right? So negation, double negation, it becomes P. Okay, so that's what happens there. The second distributive law, you distribute this over this one. So not P and P, or not P and not Q. And then because not P and P is false, yeah, we replace it by false. That's what is happening there. Commutativity. So we just rewrite it. Well, you might choose not to rewrite it really. It would be okay for me. You don't rewrite it. Just simply directly use identity law, because you have identity law for F. You have here P or F is P identity. So you have here in your problem this one or F, then that would come out. Okay, but that is our right side. Now another hint is, as you try to manipulate this one, or as you try to apply the logical equivalences, make sure that you are always thinking of the right side, so you would not go around the bush trying to solve the problem. So make this really a target for you as you apply these logical equivalences. Okay, let's proceed. You have conjunctive and disjunctive normal form. So to do this is really very important, especially when you will be learning computer science subjects, right? First is a literal. A literal is either a propositional variable or the negation of one. So for example, P and not P. That is literal. Just a proposition or the negation of it. Now we have a clause is a disjunction of literals. Disjunction meaning we use this one or. So it can be P or not, something like that. Now a formula in conjunctive normal form. Well, we also have disjunctive normal form, but yeah, we have conjunctive, we use and, disjunctive, we use or, but well, yeah, we just focus on conjunctive normal form. In your exam, I will not give you disjunctive, so focus on conjunctive. A formula in conjunctive normal form, or CNF, is a conjunction of clauses. Take a look. This one is a clause. P or not Q or R is one clause. Another clause is not P or not R. Then they are joined together by an and. So that is a conjunctive normal form. Okay? You have conjunction of clauses. Disjunctive normal form, on the other hand, is the disjunction of clauses. Take a look. Um, so to swap the definition, meaning instead of a clause having um, a disjunction of literals, then this becomes conjunction here, and you have a disjunction of these propositions here. Disjunction of conjunctions. Okay, while conjunctive normal form is conjunction of disjunction, something like that. But the more formal, you can say the conjunction of clauses, where a clause is a disjunction of these literals here. Okay, remember, clause should be ors or disjunctions, and then that is a clause, and then the conjunction of them that makes it CNF. Because in your exam, just like in this example, you're going to transform a anything or a proposition into conjunctive normal form. Fact, for every propositional formula, whatever it is, you can construct an equivalent one in conjunctive normal form. But there are ways to do that. Number one, express all other operators by conjunction, disjunction, and negation. Number two, push negations inward by De Morgan's laws and the double negation law until negations appear only in literals. Third, use the commutative, associative, and distributive laws to obtain the correct form. Fourth, simplify with domination, identity, idempotent, and negation laws. Okay? For example, you are asked, transform the following formula into CNF. So, since conjunctive normal form would be the conjunction of clauses, then these guys here, the implications should be changed into either conjunction or disjunction. That is why a while ago I said it is important for you to remember this one. Let's go back to this one. There you go. P implies Q is logically equivalent to not P or Q. So this is how you transform a P implies Q. And remember this, if you happen to see this, you just replace it by this. Or the one I told you, if you happen to see this, if and only if, then you just convert this to P implies Q and Q implies P, and then use this one. Okay? All right. Let's go to our example. You have here, we should transform that first using that identity, so it becomes not P or Q, and this one is not R or P. We use that identity or logical equivalence that I told you. And the next would be to push this negation inwards, this one here, right? So not P is P, and then change this to and not Q. Okay, I hope you can see that. This is the same here still. Next is you have the associative law or distributive laws. What happens here is, I think this is very easy to see. This guy here, not R or P, has been distributed to this conjunction. So you've got this and P, this one to distributed to not Q. So the result would be P or this one, P or not R or P, and not Q there. So you have this and here is this, not Q, and then this, not R or P. All right. Then optionally simplify by idempotent. Well, optionally, because as you can see here, this is already a clause, and disjunction of a or conjunction of clauses, that's already CNF. Actually, this is a, if you answer this one at this part, you got perfect already. Now, but well, you can simplify it because this is P or P is P, so this one is P or not R. And then for this, well, it remains the same. And by commutative and absorption laws, well, you can simplify that. You can distribute that there. You can verify that it becomes P or not R. Okay, so this is 21 over 21. That means this is the end of the slides. Thank you guys for watching or listening to our lesson in propositional logic. Up next would be the lesson in the applications of the propositional logic. So, but before that, I hope that you don't forget to click like and to like the video and subscribe so that you may get updated with our future lessons. Thank you. Goodbye.